Hello. Today, we will be discussing functions, their properties, and some special functions. So, first, before defining it, surely you have seen functions before, such as those in mathematics, where you have a graph which has the input, which is x, and your output, f of x, which will generate a graph depending on your domain and range provided for the function. Next, we also have functions in programming. You have parameters as your input, and you also have some output, if it exists, in your functions declared in whatever programming language you are using. Lastly, we also have functions to abstractify certain actions that you would want to do inside your program, which is frequently seen in pseudocode. So if we have a state or of some board and a direction where you want a certain piece to move, then it would lead you to a new state or map you to a new state. So now let's actually look into the terminologies even more. So first, we have the definition of functions. It is denoted by a mapping from set A to set B. For every element from a non-empty set A, there exists an assignment of exactly one element from another non-empty set B. It is denoted by f of A equals B, where B is the unique element of set B, assigned by f to the element A, which is an element of the set A. So for here, when we say that element A is assigned to exactly one element from another non-empty set B, here we have the element A, and for it to be a function, it should map exactly to only one element in B. And this one will be an element in A. Now, for it to not be a function, we can consider two cases. One where an input maps to more than one output, or an input does not map to any output at all. So with this, we can say that this one is a function, this one is not a function, and this one is not a function. So here in our example here, we have the three inputs of A. Let's call this 0, 1, 2. And all of them map to some output which is located in the set B. Regardless if they share the same output or not, as long as the inputs do not generate more than one output or generate no output at all, then we can say that this one is a function. So for this example, this one is a function. So let's look at more examples. So here we have set A and set B again, where the inputs have exactly one outputs to the set B. And because of this, it does not map to more than one output or to no outputs at all, then we can say that this one is also a function. So for the next example, here we have a function where we have element 0 and 1 and 2. Element 0 maps to one output in B, element 1 maps to more than one output in B, and element 2 maps to only one output in B. Because element 1 maps to two outputs in B, let's arbitrarily call them B1 and B2, which are this one and this one, then we can see that this with these relationships here, we can see that this one is not a function. So for the next example, we will have something like this. So here we have element 0, 1, and 2 again. Element 0 does not map to any output. However, elements 1 and 2 map to exactly one output in B. So since 0 does not map to any output in the set B, then we can see that this one is not a function. So for the next example, we also have something that is not a function. And that is because it violates two cases, or two cases are present in this function, quote-unquote function rather. So here we have element 0, 1, and 2, where element 0 maps to no output, element 1 maps to more than one output. However, we also have element 2 which just maps to one output. So this one's okay. However, for elements 1 and 0, this one is not okay. Therefore, this one is not a function. So now let's actually go deeper to the more formal definition of a function. For every element, so we will use symbols from predicate logic. Hopefully you remember those. From a non-empty set A, you are referring to an element from a non-empty set A. There exists an assignment of exactly one element, but we don't know which set does that element come from, and that would come from a non-empty set B. And therefore, you would have this formal definition of a function. For all elements A, there exists an element B where f of A is equal to B. So now let's look into more terminologies related to functions. First, we have the domain, which is the set A, the codomain, which is your set B. Images are those that are in the set B, and pre-images are those that are in the set A. Range consists of the set of images of A. So for range, it consists of all elements f of A such that A is an element of A. So basically, an image is basically those that are mapped by the function from some pre-image A. So all of these are mapped by some input from the set A. So these are images, and if we have something like this, if you have elements outside the range, they are not called images, but they would still be part of the codomain set B. So now let's actually have some exercises regarding these terminologies. Given a function from all real numbers to all real numbers, where f of x is 2x plus 9, determine if this is a function, and if so, find its domain, codomain, and range. So first, to determine whether it's a function, we need to review first, again, the definition. For all A, there exists B, where f of A is equal to B. So with this function, if we actually try to graph it by doing a rough sketch, notice how it actually forms a linear function because it resembles that of something like this, where you have the slope and the y-intercept and a variable of degree 1. So this is a linear function. And since it's a linear function, you would see that it does not generate more than one output for every input in the domain all real numbers. And since it's all real numbers, it would be a continuous graph where there would be no spaces in between the numbers whatsoever. And with that, since again, it does not generate more than one output, or you have to consider that it does not also generate less than one outputs, or less than one output, then this would mean that this one is a function. So now that we know that it's a function, we need to define its domain, codomain, and range. So for domain, it refers to the first set which in this case is all real numbers. Next, we need to look for the codomain. Our codomain is the second set which is being mapped to from the domain. So that would be all real numbers as well. And then we have our range. So what would be our range? In mathematics, range refers to the set of values generated by the function, or all the outputs made by the function. And since your input is a real number, your output could also be a real number. So that means that this one would be uh, all real numbers in terms of its range. So that would be our first example regarding functions. So let's have another example here. So what if we change the set this time? We have a function from integers to real numbers where f of x is equal to 2x plus 9. Determine if it's a function, and if so, find the domain, codomain, and range. So here, it says that our inputs are integers, which means we cannot use those in between the integers, or rational, irrational numbers, or basically, um, yeah, rational and irrational numbers. So if you have 1 and 2 here, we could probably have like 1/2 here or square root of 2 here, which we will not use in graphing the said function. With this, we would actually generate an output that would look something like this. It would look like a line, but we do not actually connect the lines because real numbers, not real numbers, I'm so sorry, rational numbers and irrational numbers are not defined as inputs for this function. So this is what the graph would somehow look like. And because of this, we also notice that for every input, it only generates exactly one output because it's still a linear function. So because of this, we can say that this one is a function. And if it is, we need to find the domain, codomain, and range. So let's first start with the domain. Our domain here is z, which is all integers. Next, we have our codomain, which is the outputs, the possible outputs generated by the function. So that would be real numbers, or basically where all the outputs would belong to. And we have the range, which is the actual values generated by the function. So as you notice, since our inputs are integers, and you multiply that to an integer 2, and then add it to another integer, which is 9, you should get an integer, or something that is in integer. Because if you have something like 2x plus 9, and this one is an integer, it's not possible for you to generate something like pi, e, 1/2, square root of 3. It would not be possible at all. So with this, your output would be all integers. So hopefully that clears up the difference between codomain and range. So to review once more, codomain is where your output could belong to. So it's basically the set where all your possible outputs could belong to. And then for range, it's the actual the set where your all out actual outputs belong to. Alright, so now that's done, we've hopefully cleared the difference between codomain and range. So let's proceed to another item. So here, given the function from all real numbers to all real numbers, where f of x is equal to 1 over x, determine if this is a function. And then if it's so, then do the same thing, find the domain, codomain, and range. So here, we can sort of graph this. And if this function is familiar to you, it's actually a rational function with an asymptote, two of them actually, one at x equals 0 and one at y equals 0. So we need to determine whether this is a function. So we know that f of 0 does not match to any real number as an output. And so, since 0 does not match to anything whatsoever, this one is not a function. However, if you remember from your senior high or mathematics in general, if you have a function, to determine whether it is a function, you apply the vertical line test. And if it passes through more than one point, then this one would not be a function. Since uh, if we apply a vertical line test to any point in the x-axis on this function, we could say that this one could be a function. However, based on our actual definition of a function, for all values that are inputs, there exists an output where f of a matches to some output b. But because 0, if we say a is 0, we need to find some element b that would make this true. But because no element in the set of real numbers would make this true, then this one would be false. And therefore, the entire statement would be false. And if the entire statement is false, then this one is not a function. So with that, we cannot determine its domain. We can determine its domain and codomain, but we will never find out its range. Because again, this one is not a function. Let's try something else. We have positive integers mapped to real numbers. So to determine whether this one is a function, let's graph this one, which would look something like, wait a minute, something like this. So, is it a function? Well, our inputs are positive integers, so we do not have to worry about 0 in this case, which would make the function, the output undefined. So, if our input is all positive integers, our outputs would exist in the codomain. So therefore, this one would be a function. For all elements which are part of positive integers, there exists a b where f of a is equal to b, which in this case is all real numbers. And because that is true, then we can see that this one is a function. If so, we need to define its domain, codomain, and range. So to find its domain, we'll shortcut it to this, codomain and range. Our domain is all positive integers. Our codomain is all real numbers. over here. And our range, as you notice, if we actually try to input the values, f of 1 is equal to 1, f of 2 is equal to 1 half, f of 3 is equal to 1/3, and so on and so forth. And as you can see, they're actually all rational numbers because aside from them not being irrational, it's actually a ratio of two integers where you have the denominator being 1 and your denominator being any positive integer. And with that, this one is actually belonging to the set of rational numbers. So this one would be all rational numbers, or Q. So what if it's from positive integers to integers? So again, we need to define whether it's a function or not, and if so, find the domain, codomain, and range. So with this, we showed a while ago that our inputs as positive integers generate rational numbers as output from a while ago. Because we did not change the domain for this example, it still remains as positive integers. And since our range, well, not range first, our codomain is said to be integers. This would actually not be a function. Why? Because this is, we have actually a counterexample for this. So if we have f of 2, that would result to 1/2. However, since our codomain is integers, if we have integers over here, our output 1/2, let's say it's over here, is actually outside of the codomain, which means that this one is not belonging to the codomain and therefore is not a function. So with that, please take note to observe the function, your possible inputs, your possible outputs based on the defined domain, codomain, and if it is a function, the range of the function. So here are some challenge exercises for you to do to determine whether something is a function or not. Take note, since we are earlier I said that this is from one set to another set, this one would be valid as your domain or your codomain. Additionally, you can also use set operations to define certain domains or codomains of your liking. So you can have something like this as your domain, or something like this as your codomain. It can vary. So try this as your exercise. So now let's focus on the properties of functions. First, we have injective functions, which are one-to-one, where for all of A, for all of B, if f of A is equal to f of B, then that implies that A is equal to B, where A and B are both in the domain. To make it simpler, this just means that same outputs imply same inputs. Contrapositively, we can say that if the inputs are not equal, then the outputs are not equal. Or different inputs imply different outputs. So let's have an example here. So we have elements 0, 1, and 2. And notice how they do not share any same output in the codomain. So let's say this one is 3, this one is 5, this one is 7. 0 maps to 7, 1 maps to 3, and 2 maps to 5. And based on our definition, for all elements A and B, if the outputs are equal, then that means that the inputs are the same. Contrapositively, which would be more applicable for this case, if our inputs are not the same, so should their outputs. And if we actually try to look at by applying this statement over here, notice how the outputs are not the same for every input. Therefore, we can say that this function is injective. So let's have some other examples. Here we have, let's say again, element 0, 1, 2, and then this one would be 3 and 5. So 0 maps to 3, 1 maps to 3, and 2 maps to 5. So let's follow this contrapositive statement over here. If your inputs are not the same, then that means that their outputs are also not the same. However, this would be actually false. Why is that so? Notice how 0 and 1 are different, which would make this correct, but they have the same output, which makes this false. So if this is true, and this one is false, with implication statements, something like this would result to false. Therefore, this function would not be injective, because two inputs share the same output. So let's go to another example. If we have elements 0, 1, and 2, and then we have element 4. 0 maps to 4, 1 maps to 4, 2 maps to 4. Is mapped to 4. So with this, we can see again, these inputs share the same output. And because of that, we can say that this function is not an injective function. Okay, so let's proceed to the next example. Here, without actually me showing the mapping, you could see that this is actually a one-to-one function, because for every input, they do not share the same outputs, which means that this one is an injective function. So now let's proceed to another property of functions, which are surjective functions, where it states that for all B, there exists an element A in the domain where f of A is equal to B. Or in short, all outputs can be produced by some input, which means no element in the codomain should be left behind when applying the function. A counterexample for this, or something that would make the statement false, is there exists an element B where for all of A, no element of A would produce B, or would produce some element in the codomain. So let's look at this example here. For every element in the domain, they map to some output in the codomain. And notice that our codomain is equal to something else. because since all outputs are taken, or all elements in the codomain are taken into account, that means the range would also be equal to the codomain. So something to take note for surjective functions, make sure that the codomain is actually equal to the range. So let's have some more examples over here. So we have our inputs mapping to some output in the codomain B. However, we have an element over here which is not mapped by any input in the domain. So to see more clearly how this is represented with this counterexample, there exists a B, which is this one, that for all of A, all elements of A over here, f of A cannot map to the said value B. And since none of the values in the domain actually are equal to this element in the codomain, this one would be true. And if this one is true, therefore this statement would be false. Therefore, this function is not surjective. So let's have another example over here. For all elements of A, notice that they all are mapped to some output in B, and since all elements in B are not left behind, or basically, it's just saying that the codomain, which is B, is equal to the range, which is the set of all values f of A such that A is part of the codomain. Therefore, we can say that this function is actually surjective. So let's proceed to another example. So here, we have a function which maps every input to some output in B. So since all elements in B are being mapped by some value in the codomain, we can say that this one is surjective. Take note that although this function is not one-to-one, because two inputs share the same output, it wouldn't matter anyway, because our focus for surjective functions is to make sure that the codomain is equal to the range. Assuming that codomain B consists of three elements only, then we can say that the codomain is equal to the range. Additionally, since we're focusing on the codomain for surjective functions, we need to take note that for all elements of B, it needs to be mapped by at least one element in A, or the domain. And since it satisfies that property, then this function would be surjective. So now let's actually combine injective and surjective functions together to form bijective functions, or a one-to-one correspondence. It basically is both injective and surjective in nature, which means one, all inputs do not share the same output, and number two, all outputs which are part of the codomain are mapped by some value in the domain, or in simpler terms, all outputs are generated by some input. or all outputs are not left behind. So how can we determine a counterexample for this? For it to not be bijective, it's actually simple. It needs to be not injective or not surjective, or neither injective or surjective. So in this case, we have a function over here where for every input in the domain is mapped to all elements in the codomain. And since our codomain is equal to the range, assuming that the codomain has only 3 elements, then we can say that it is an onto function. Additionally, we can also say that it is one-to-one because the inputs do not share the same output. So with that, it's also injective. Therefore, it is also a bijective function. So let's look at other examples regarding this. So here we have a function where we have inputs mapping to some outputs in the codomain. So notice how number 1, 2 inputs map to the same output. So let's call this 0, 1, and then let's call this 5. So since 0 maps to 5, 1 maps to 5, they share the same output, but the inputs are different. Therefore, they're not injective, which would automatically mean that this function is not bijective. Additionally, we can also see that there is some value in B that is not mapped by the function from any element in A. So if you have, let's say, 7, 7 over here is not mapped by any value in A, because there is no value in the domain which can actually help you get to the value 7. So therefore, it's also not surjective or not onto. But it's still a function that isn't injective, surjective, or even bijective. But it's still a function regardless. So let's have another example over here where we have here we have our values in the domain and our values in the codomain. So here we can see that already that all outputs or all outputs in which are part of the range is equal to our codomain, which would make this surjective. However, this would not be injective because 2 inputs, this one and this one, map to the same output. And because of that, this one is not bijective. So let's look at other examples. Here, we also have another function. And notice how this value over here is not being mapped by the function based on some value in the domain, which would make this not surjective, but it would still be injective because all our values in the domain map to some different value in the codomain which they do not share. So while it is not surjective but it is injective, it's still not bijective. So let's have some exercises regarding the properties of functions. Let's have number 1 here only as our example. The rest you can do on your own. So here, we have a function from R to R where f of x is equal to x squared minus 1. Notice how x squared minus 1 just looks like a parabola. So here, let's focus on the injective property first. So, for it to be injective, no two values as inputs should share the same output. So if we try something like f of, let's not do it here, let's do it here, below. Let's say f of 1, that's equal to 1 minus 1, or 1 squared minus 1, which is equal to 0. F of negative 1 is equal to negative 1 squared, which is just positive 1 minus 1 is 0. Notice how our inputs are different, but we result to the same output. And because of that, this is not injective. And we need to provide a counterexample for this. So using our example below, we can say that f of 1 is equal to f of negative 1, which is equal to 0. This is our counterexample for the injective property on why it is not being satisfied. And with that, we can just say that this is not bijective because it's already not injective. Next, is it a surjective function? Well, let's check. Since our out codomain is all real numbers, we expect that for it to be an onto function, all values in the codomain are being accounted for in the range. But let's say we have, let's say f of let's say we have an arbitrary value here equals 23. Is there such value of a in all real numbers that would generate 23? There would be actually, because that's actually square root of 24. If we square that value minus 1, that would equal to 23. So let's try something else to determine whether this function is onto or not. We have, let's say, negative 5. Can you find a value that would generate negative 5 given that your input belongs to the domain all real numbers? So if we try like a negative number, you would get a positive number actually, because it would, if you have a negative number, sabihin natin negative a, square it, you'll get a squared. But if you have, let's say, 0, f of 0, this would become 0 squared minus 1 is negative 1. So this would be one of the negative values that you can get, but this is actually the minimum value or the lowest value that you can get using the function. And with that, because there is no value that you can get to negative 5, then we can say that no such value of a can reach you to negative 5. Therefore, it's also not a surjective function. So the other functions will be left as an exercise to you to determine whether something is injective, surjective, or even bijective. And these are some challenge exercises that you can use to determine whether something is injective, surjective, or bijective. Take note that functions can have more than one input, which is represented by the cross product of two sets over here, which is in this case, real number, cross product by a real number. Next, we have here, we have a piecewise function. which is a function that has different not necessarily continuous when you create the graph, something like this. So although a piecewise function is not connected, you can still determine whether that function is injective, surjective, or bijective. Another thing to note with this exercise and the previous exercise, there is a function that is actually not a function, and that is up to you to find out which one would that be and why it's not a function. So now, let's proceed to inverse functions. So notice we'll go back to bijective functions, which are again injective and surjective in nature. And if a function is bijective, then we can see that this function is actually invertible. So let's define inverse functions. First, given a bijective function, f, which maps from a to b, where f of a is equal to b, it assigns an element b to the unique element a in the set A, denoted by the inverse function f of b equals a. So our previous examples show that this our codomain A, actually not codomain, I'm so sorry. This is domain and mapping to the codomain using the function f with a as our input to some value in b. On the other hand, inverse functions actually get you back to the original value. So this time our domain would be the codomain, and our codomain would be the original domain. So altogether, think of inverse functions as a way, as some portal, I guess, that would transport you from one set to another set and get you back to the original value that you came from with the said function. So an example of an inverse function would be something like this. You are given a function f which maps from the set of, let's say that this is the set of all uppercase letters and let's say L is the set of lowercase letters. So with this, we can actually illustrate the function originally. So if we have, say, f of a, it basically turns the uppercase letter into a lowercase letter. So over here, we have f of a equals a. So if this is u, and this one's L, and we say that this one is a, and then this one is small a. Using the function, you can actually get to your desired output, which is the lowercase a. The inverse function, on the other hand, can transport you back to the original value that you came from, which is the inverse function. So basically, that is the unique property of bijective functions, with it being invertible. You can basically get from one input to another output and then go back to the same input. And when you apply the function and inverse function, you get the same results every time. So if I do f of a, I go back to small a. Then if I use f of negative 1a, I go back to capital A. And then if I go back to f of a again, I would get lowercase a. So it should be the same output every time you use the function or inverse function. Another example is the linear function f of x equals 2x plus 1. So in Gen Math, in senior high, maybe you've learned how to actually convert functions to its inverse counterparts. So if you have y equals 2x plus 1, which is the same as f of x over here, we swap the values of x and y and then isolate y once more. So this would become x minus 1 equals 2y, and this would result to x over 2 minus 1 half equals y. So let's say we have f of 3. F of 3 would be 6 plus 1 equals 7. So what we expect with this function over here is that f of negative 1, 7 should get you back to 3. So let's try actually doing it, where f of negative 1, y, is equal to x over 2 minus 1 half. Let's not confuse ourselves. Let's just put this as is. Okay. So our input, which is our x over here, should be 7. So let's substitute x with 7. So this would become 7 over 2 minus 1 half. And this would actually equal to 6 over 2. And simplifying it would get you back to 3. And because this is what our actual result is 3, that means this function and this function are inverses of each other. Or we can say that f of x is invertible. So what would happen then if a function is not injective or surjective? So let's say we have some arbitrary function grayscale, which basically transforms these colored circles into its grayscale counterparts. So let's say we input them into this function, and let's say our output would be something like this. So since the red and blue circles generated the same output, this is an not injective function. So let's look further. So will the result be a red or blue circle if we take the inverse of that said output? So if we transform this black circle back to its original form, would it generate a red circle? Or would it generate a blue circle? Notice how it could have two outputs, or some input is mapped to two outputs. And since this, by definition, is not a function as we observed earlier, this grayscale inverse function is not a function, which would mean one thing, that non-injective functions are not invertible. Because as we have seen a while ago, this inverse grayscale function, it maps to more than one value, which means it's not a function. Therefore, non-injective functions are not invertible. Let's have another one. Given a function f from all natural numbers to all natural numbers, for this video, we will consider natural numbers starting with 0, 1, and so on, where f of x is equal to x plus 1. So our inputs here, 0 maps to 1 and 1 maps to 2. So first, before anything else, we need to find out what is the inverse of f of x. So like what we did a while ago, swap the positions of x and y, and then isolate y, which would get you x minus 1 equals y, which is, as in this case, this output over here, f of negative 1, x equals x minus 1. So then, we apply the function from set B to set A, and we get 2 minus 1 equals 1, 1 minus 1 is 0. Then what is the inverse function when applied to 0? If we just apply it as is, f of negative 1, 0 is equal to negative 1. However, our codomain, which is for this one, codomain for the inverse function, take note, negative 1 is not an element of the set of natural numbers. And because of this, it would not generate any output, or some output in B does not map to any output in A, which means that this is not a function as well if we take the inverse, given that our domain and codomain are both natural numbers. Therefore, non-surjective functions are not invertible. So again, when we determine whether a function is invertible or not, we have to look into the function and its codomain and domain to determine whether it is invertible or not. So now we will proceed with the special functions. So first, we have the floor function denoted by this sign over here, and it pertains to the largest integer less than or equal to x, which may sound confusing at first, but we will visualize it this way. So first, we have some arbitrary value, let's say 2.05. Where this one is 2 and this one is 3. So when we say floor function, when we apply it to x over here, we are looking for the first values less than or equal to x. So all values less than or equal to x will be candidates for the value of the floor of x. Next, we take into account this time those that are integers that are less than or equal to x. So we have our values over here from negative 1 to 2, which are less than or equal to x, and they are also integers. And then from there, we get the largest integer less than or equal to x. And because 2 is the largest integer compared to values 1, 0, negative 1, and 2, we can say that the floor function of 2.05 is equal to 2. Okay, so let's proceed to the other function, the ceiling function. This time, it pertains to the smallest integer greater than or equal to x. So let's say this again is 2.05, and this one is 3, this one is 2. So when we say the smallest integer greater than or equal to x, first again, look for the values greater than or equal to x. So that's all of the values over here shaded in this interval, which may be integers, rational numbers, or irrational numbers. So then we pertain to the not smallest yet, but integers greater than or equal to x. We have 3, 4, 5, and 6, which will be candidates for what the possible value of the ceiling function might be applied to 2.05. And with that, our ceiling value would be the smallest integer greater than or equal to x. Since it falls under 3, That means our ceiling function means that it is 3. And that is for ceiling functions and floor functions. Here are some examples that you can look into regarding floor and ceiling functions. Notice how floor functions, you are rounding down to the smallest integer, or you are rounding up to the smallest greatest integer. And then for floor functions, it's actually rounding down to the largest integer less than or equal to the input over here. And it also applies to negative numbers. A floor function, let's say this is your x, you would go further. So this would be your, if this was negative x, this would be your floor function. And this one would be your ceiling function when you apply to a negative number. And if it's a whole number, you basically just maintain the same value. So you can look further into the value examples over here, and that is it. So for exercises, you need to evaluate the following items over here, and to also look into the properties of functions applied to the floor and ceiling functions. Is the ceiling function bijective? How about the floor function? So that is all for this video regarding functions.